Okay, it looks like we're ready to get started. If you have any questions now or during the live chat, you can type them into the chat bar. So don't hesitate to do that. There is a little bit of a delay sometimes between when I speak and when you hear it. So just be patient and I'll respond to your questions. Okay. All right, so we're going to talk about concavity today. But before we do, I just want to make sure that everybody's clear on when a function is increasing or decreasing and how that relates to the first derivative. That's going to be important. That's from section 4.1. That's going to be important for understanding the next section. So, for example, let's look at a function that we are all probably pretty familiar with, which is the function f of x equals x squared. And we're going to use the first derivative to determine where f is increasing or decreasing. Okay, and now when I say where f is increasing or decreasing, I am talking about intervals of x values. So before we start this calculus problem, let's recall what we know about the function x squared. So you know it's a parabola. It goes through 0, 0, goes through 1, 1, and negative 1, 1. And it's opening upward. Okay, so here's the graph of f of x equals x squared. So you should be able to tell me by just looking at the graph. Oh, and by the way, could you just go ahead and just type yes if you can hear me? So I want to make sure that I'm reaching everybody. Okay, so on the graph of f of x equals x squared, where do we see that the graph is increasing? So increasing, remember we always read a graph from left to right. So increasing, thank you, thanks for typing yes. So increasing means going from low to high, that's increasing. While decreasing means going from high to low, from left to right. So on this graph, on the right side, we see that the graph is increasing. We start low and we go high. So increasing on the right from 0 to infinity. These are x values, so that's where the graph is increasing. On the left, on the other hand, we're going from high down to low if we go left to right. So we would say that this function is decreasing on the interval from negative infinity to 0. Okay, well, how does that relate to the first derivative? Well, the first derivative is the slope of any given tangent line. So for example, here on the right-hand side, if we look at the slope of this tangent line, we would observe that the slope must be positive. So that means that if we were to find a value for f prime at that point, then we would get a positive value. On the other hand, on the left, if I were to draw in a tangent line, this would be a downward slope, and that's because the function's decreasing. And so what that means is that the slope of the tangent line is negative. So any value of f prime that you would get by plugging in something to the left of 0 would give you a negative value. And then if you look in between the two where they meet at 0, we have a horizontal tangent line where the slope is equal to 0. So now let's pretend like for a moment like we don't know this, that we don't know that f is increasing to the right of 0 and decreasing to the left. So it must have a positive derivative on the right of 0 and a negative on the left. Let's go back and look at this calculus question. So if you were just given the equation of the graph and you didn't know anything about the graph, how would you use f prime to determine increasing or decreasing? Well, in reverse, we would know if f prime is negative, the function is decreasing, and if f prime is positive, the derivative is positive, the function is decreasing. So the technique is to use a sign chart for f prime to find out where the function is increasing or decreasing. So what is f prime in this case? So the derivative of x squared is just going to be 2x to the first, or 2x. We would find anywhere that that's equal to 0 or undefined, because that would be the only place the sign can change from positive to negative. So I set 2x equals 0, divide by 2. X equals 0 is the only place where the sign might change. You would then make a sign chart that represents all the f prime of x values at a given value of x. We know that when x is 0, f prime of x is 0 also. And then we would just test points on either side, and we would say, okay, if x is -1, we would get -2. So all the values to the left of 0 are going to yield negative derivative values. And then if we plug in a positive value, we get positive values. So this sign chart, which represents the values you get from plugging into the derivative, tells us something about the function f of x. It tells us that the function y equals f of x is decreasing to the left of 0 and increasing to the right. By the way, when a function changes from decreasing to increasing by going through a slope of 0, you know that you have a relative minimum or a local minimum at that value. Okay, but there's more to the shape of the graph than just whether it's increasing or decreasing. And that shape, the curvature of the graph, is what we're going to be concerned about today. So moving on to section 4.2, and again, if you have any questions, feel free to interject. So in section 4.2, we're going to be looking at how we could have two different functions, both of which are decreasing, but their shape could look different. Okay, so here I have drawn two graphs. Both of them are decreasing. They start high and go low, but the graphs are not shaped the same way. They curve in different directions. So we consider a curve that looks like it could almost hold water, like a part of a cup facing upward. We call that concave up. And a curve that looks like that it would pour water out, that it's part of a cup turned upside down, we call that concave down. And so if you look back at the graph of f of x equals x squared, you can see that that guy was concave up all over the whole graph, right? It looks like a cup facing upward, like it could hold water. All right, so what relationship might that have to the derivative? We know that the sign of the derivative doesn't tell us anything about whether it's concave up or concave down. It only tells us increasing or decreasing. Right? Both of these are these segments that I've drawn here of a function. Both of these are decreasing, so their first derivative would be negative. But what else could we observe? What difference could we observe in the values of the derivative? So what I'm going to do now, actually, let me leave that up there. I'm going to draw some different graphs that are concave up. that one of them is increasing and one of them is decreasing. So concave up increasing looks like this. Concave up decreasing looks like this. And then you could have a graph that is a mixture of increasing and decreasing, and it's still concave up everywhere. So like maybe it starts out, let's see. Well, we already saw that that would be the parabola, right? It would be like a parabola. Okay, so this graph on the left is increasing. The graph in the middle is decreasing. And the graph on the right is a mix. But they all are concave up. So what relationship does that have to the slope of their tangent lines? Let's see if there even is one. So we'll look at the first graph. Okay, the slope of the tangent line at the very bottom appears to be 0. Then we have positive slopes. Maybe this slope is 1, but then this slope is a little steeper, so maybe it's 2. So the slopes look like they're increasing, 0, 1, 2, and so on. Now you might think, well, the slopes won't be increasing on this middle graph, but let's take a look. If we start at the left, we're going to have a very steep slope, but it's negative, right? So maybe it's like -2. And then if we go a little further along the graph around the middle, the slope could be maybe -1. And then the slope equaling 0 here. So that's -2, -1, and then 0. So notice that again, from left to right, the values actually are increasing. In the first graph, they were all positive. In the second graph, they're negative, but they're both increasing. Okay, so Joshua asked a good question, like why would we be concerned about the concavity? So I'm going to deviate from this explanation for just a minute, and I'm going to say, what if I had a function that represented sales? Let's go back up to the top, actually. Okay. All right, so let's say that we're talking about sales. And let's say that I have a function that represents the sales on a given month or day or whatever. And the graph looks like this. Okay, so this is what happens on a certain date, let's say January 1st. Okay, so prior to January 1st, the sales are increasing, but not only are they increasing, each day that goes by, it appears that they're increasing at an even faster rate. The slope, rate of change of the sales is increasing faster and faster. But then on January 1st, something changes. The slopes or rates of change of the sales are decreasing. The sales themselves are still going up, but they're not going up nearly as quickly. So why might that be important? Can anyone answer that question maybe in the live chat? Could you explain why it might be important that to us to observe that while the sales are still increasing, the slope, the derivative, the first derivative is positive all over here. The rate of change of those slopes has changed. So it's a change in the rate of change. It's a second derivative. Let me ask you this. Where would you rather be as far as how your sales are changing if you're owning a company? Would you rather be on the left side of this graph Or would you rather be on the right side of this graph? Any ideas, anybody? Okay, yeah, so on the left, we're changing our rate of growth of our sales is increasing steadily, but then all of a sudden it starts to slow down. And so that's an indication that we don't expect as much of a growth in our sales. And so that is going to affect our planning for our business and that sort of thing. So yeah, it is a way to try to predict a change in the rate of change. Exactly. So the first derivative is a rate of change of the function, while the second derivative is a rate of change of that rate of change. Okay, so let's go back to the scenarios where we had concave up. In the first function, we had concave up increasing. Second, we had concave up but decreasing. In both cases, the slopes, though, were increasing. The slopes are getting to be larger values. Let's look at the last situation where we have a parabola here. So maybe we have a slope of -2, and then a slope of -1, and then a slope of 0, and then a slope of 1, and then a slope of 2. Okay, so if your slope is going from -2 to -1 to 0 to 1 to 2, again, it's increasing. So if your slopes are increasing, then the derivative of your slope should be positive. F prime is increasing. F prime is increasing in all three of these situations, regardless of whether the function f is increasing. There's no connection. The derivative is increasing, the slopes, the rates of change are increasing, then that means we know that if you take the derivative of that function f prime, it should be positive. So if you're ever trying to figure out where a function is concave up, where f, the original function, is concave up, that's going to happen where f prime is increasing, which means that the second derivative is positive. Okay? All right. And as you probably could guess, I could draw similar graphs for concave down. Anytime the original function f is concave down, that means that the derivative is decreasing, which means its derivative is negative. Okay. So let's go ahead and determine the intervals on which a particular function will be concave up or concave down. So we're going to determine the intervals, and those would be intervals of x values, on which the graph of f of x equals x squared plus 1 over x squared minus 4 is concave up or concave down. Okay, so whenever you see that you have to determine concave up or concave down, what that really means is where is the second derivative positive or where is the second derivative negative. And the only way that it can change from positive to negative is to go through 0 or undefined. So the first thing you're going to need to do is find f prime of x, use that to find f double prime of x. Then you're going to have to find any values of x such that the second derivative is either equal to 0 or undefined. And then you're going to make a sign chart for f double prime and use that sign chart to identify intervals and answer the question. So the answer to the question will be when f double prime is positive, that means that f is concave up. And whenever we have an interval where f double prime is negative, that would mean that f is concave down. All right, so let's try and do this. All right, what kind of rule would we need to use to find the derivative of f of x equals x squared plus 1 over x squared minus 4? Any ideas on that one? How do you take the derivative of that function? Very good. Quotient rule, right? So I like to think of the quotient rule as saying that the derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. In this case, the top function is x squared plus 1. So the derivative of the top is 2x. And the bottom function is x squared minus 4. So the derivative of the bottom is also 2x. So let's fill that in. The derivative f prime of x is going to be x squared minus 4 times 2x minus x squared plus 1 times 2x all over x squared minus 4 squared. All right, now the next thing you should always do when you're working with a quotient rule is you want to look at the top and you want to look at the two terms that are created using the quotient rule and see if you can factor out a GCF, because that makes it easier to work with. So let's see what we have here. We have f prime of x equals, we have a 2x in common, so I'm going to factor out a 2x. And what's left behind in the first term is x squared minus 4. What's left behind in the second term is x squared plus 1. And then whatever's left in the brackets here, you could simplify as much as possible. So in this case, we're going to have f prime of x equals 2x times negative 4 minus 1 is negative 5 over x squared minus 4 squared. Or we could simplify that a bit, negative 10x over x squared minus 4 squared. Okay? All right, so that's the first derivative. If we were analyzing whether the original function were increasing or decreasing, we would analyze the first derivative, but we're not. We've been asked to find where we have concave up or concave down. So we have to take the derivative of the derivative, or the second derivative. And once again, this is a format which lends itself to the quotient rule. So we're going to use bottom d top minus top d bottom over bottom squared. The top function is negative 10x, so its derivative is just negative 10. The bottom function is x squared minus 4 squared. So that means its derivative, we'll have to use the chain rule or FOIL it out, but I'm going to use the chain rule. So I'm going to bring the 2 out front, subtract 1 from it, and then multiply by the derivative of x squared minus 4, which would be 2x. So this is going to be 4x times x squared minus 4. All right, let's see what we can do with that. So filling in the formula, we have the second derivative equals the bottom, which is x squared minus 4 quantity squared, times the derivative of the top, which is negative 10, minus the top, which is negative 10x, times the derivative of the bottom, which is 4x times x squared minus 4, all over the bottom squared, which is x squared minus 4 squared squared, so to the 4th power. Once again, it's easiest to work with if we look at the top of the numerator and try to see what's in common between the term on the left and the term on the right. Okay. So what could we factor out there? Let's see. Minus a minus is a plus, so it doesn't really matter. We could factor out a positive 10 or a negative 10. I'm going to just factor out a positive 10. We can also factor out x squared minus 4 to the lower power. The lower power is 1, and that's about it. So let's see what's left behind. In the first term, we took out everything but a negative 1 and 1 factor of x squared minus 4. Plus, in the second term, we took out the 10, but we're left with x times x is x squared, so 4x squared. We took out x squared minus 4, though. That's gone. Okay? And then now we are going to simplify wherever possible. So for example, this x squared minus 4, there's a power of 1 there. We are left with 3 in the bottom. And then this part right here, let's see, we have negative x squared plus 4x squared. So that's going to be 3x squared plus 4. So we have 10 times 3x squared plus 4 over x squared minus 4 cubed. Okay, so let's take a little inventory of what we've done so far. So remember, we need to find the first derivative, which we did using the quotient rule, and we simplified it. And then we took the second derivative using the quotient rule. Now we're on the third step where we need to set the second derivative equal to 0 or find where it's undefined. Whenever you have a rational function, a function in the form of a fraction, wherever the numerator equals 0 is where the function itself equals 0. So if we want to know where the second derivative equals 0, we set the numerator equal to 0. If we want to know where the second derivative is undefined, we have to set the denominator, the bottom, equal to 0. So let's see. If we set the numerator equal to 0, we have 10 times 3x squared plus 4 equals 0. All right, it is impossible for 10 to equal 0, but I'm going to write it anyway because you set each factor to 0. So we have 10 equals 0 or 3x squared plus 4 equals 0. That can't happen. Let's see what happens here. We get 3x squared equals negative 4. That means x squared equals negative 4/3. X would have to be an imaginary number. So there are no real value x's for which the numerator would equal 0. So it doesn't happen. Okay, and then where would it be undefined? Well, that would be where the denominator equals 0. So x squared minus 4 cubed equals 0. But the only way that can happen is if x squared minus 4 equals 0, which would mean x squared is 4, which would mean x is plus or minus the square root of 4. So x would be plus or minus 2. So this is where the second derivative is undefined. All right, so again, taking inventory of where we are, we have just figured out the x values for which the derivative is 0 or undefined. There are only two, negative 2 and 2, and the second derivative is undefined there. So now we're going to use that to make a sign chart. All right, so the sign chart is just a number line that has x values on the bottom and f double prime of x values on the top. And so put the x values we have found in numerical order. And then since we found that the second derivative was undefined there, put a u on the top. And now we're going to check points in between. So negative 3, 0, and 3, for example. It really doesn't matter, just do something that's relatively easy arithmetic-wise. Now remember, the second derivative is this expression here. I observe that no matter what I plug in for x, the numerator of that expression is going to be positive. So I'm just going to say, okay, if I plug in f double prime of -3, yes, Joshua, it is very algebra intensive. That's true. It's probably the biggest challenge in this section. All right, so f double prime of -3 is going to be, I don't care what the actual value is, but when I plug it in, I know I'm going to get a positive over something. So that's going to be a positive over, and then we're going to have 9 minus 4 cubed. So that's going to be a positive over a positive, which is a positive. So we get positives here. Plugging in f double prime of 0, we're going to get positive over, and we're going to have 0 squared minus 4 cubed. That's a positive over a negative, which is a negative. So we're going to have negatives here. And then if I plug in 3, we have f double prime of 3 equals positive over, and again we're going to get 9 minus 4 cubed. So that's positive over positive, which is positive. So our sign chart is complete. And all we have to do now is to read off the sign chart our solution. We know that wherever the second derivative is positive, the original function f will be concave up. F double prime is positive on the interval from -infinity to -2 over here, but it's also positive to the right of 2 from 2 to infinity. So what that means is our function f is concave up on these intervals. So that's part of our answer. The other part is, where is it concave down? That's going to be wherever we have negatives. So where f double prime is negative, we know that f is concave down, and that's on the interval from -2 to 2. So I'm going to zoom out here so you can just kind of see. It's a long problem, right? But you just have to, like with everything else, you have to take it one step at a time. One of the big things people have trouble with is the step from here to here, where we're factoring out a GCF. So what you want to keep in mind there is just look for any factors, that's things in parentheses essentially, things that are being multiplied, that they have in common, and factor it out to the lowest power. All right, any questions about that one? Okay, by the way, just so you know, this function -4, you probably realize that it has a vertical asymptote at -2 and a vertical asymptote at 2. It also, the limit to infinity is 1 over 1 is 1, so it's going to have a horizontal asymptote at 1. And it's concave up prior to -2 and after 2. And it's concave down in between. And if you plot points, you're going to get something like this. So this is our first step into really getting very specific about the shape of the graph. Not just where it's increasing or decreasing, not just individual XY coordinates, but the curvature. Okay, the next thing that I want to talk about is inflection points. Okay, so an inflection point is a point where the concavity changes. The function has to be defined at that point though. So, for example here, this point, let's say this is A, x value A, so this would be the point A comma f of A. This point is an inflection point because the graph changes from looking like it could hold water, like part of a cup facing upward, to looking like it would spill water out, a part of a cup facing downward. So this guy here is a point of inflection or an inflection point. Okay, it's a point where the function changes from concave up to concave down. Concave up to concave down. So how do you think you could find an inflection point? What would you use to find a point where a function changes from concave up to concave down? Any ideas? Well, it definitely has to do with the second derivative, right? The second derivative tells us about concave up and concave down. My chat here. Okay, so yeah, so slope of infinity would definitely, could potentially cause an inflection point. And we're definitely interested in where the sign of the second derivative changes. Remember, signs on a sign chart can only change if we go through 0 or undefined. So a slope of infinity would be an undefined slope, right? And then 0, a slope of 0 could also, second derivative slope of 0, I should say, is also a place where the concavity could change. So what we're going to do is look, just like we did a minute ago, for the points where the second derivative is 0 or undefined. And then instead of just saying, okay, before we were just looking for which intervals were concave up and concave down, what we're going to be looking for is for which of those values where it actually equals, well, I don't even want to say that. We're going to look for values where the function is defined and then we have a change from concave up to concave down. So yeah, the sign of the second derivative changes. So I just want to emphasize though, we're going to look for x values where the original function is defined, so it can't be undefined, and the second derivative of x changes sign. And that can only happen where the second derivative is 0 or undefined. Okay, so let's look at an example. Trying to, here we go. Find any inflection points. Okay, the steps are going to be pretty much the same as in the last problem. First, we need to find f prime of x. So that's going to be negative 15x to the fourth plus 15x squared. Then we're going to need to find the second derivative f double prime of x. That's going to be negative 60x cubed plus 30x. Then we're going to find where the second derivative is 0 or undefined. In this case, it's a polynomial function, which is defined everywhere. And it's important to note that the domain of the function f is also negative infinity to infinity. There are no points where the function is undefined. All right, so that means if the second derivative also is never undefined, we just need to find where it equals 0 to find any potential inflection points. So this is a polynomial function of degree 3. An effective way to deal with solving this equation is to factor. I noticed that we have a factor of 30x in common to the two terms. That's going to leave negative 2x squared plus 1 behind when we factor that out. So the only place where the second derivative might equal 0 is where 30x is 0 or where negative 2x squared plus 1 is 0. So Joshua was asking if the inflection point is essentially where the slope of the original function begins to decrease. I would say it's essentially where the slope of the original function changes from either increasing to decreasing or vice versa. Does that make sense? Okay, so 30x equals 0 would mean x is 0, and negative 2x squared plus 1 equals 0 would mean that x squared equals 1/2, which would mean that x is equal to hold on one second. Yeah, that's right. So that would mean that x is equal to plus or minus the square root of 1/2, which would mean that x is equal to plus or minus 1 over the square root of 2. Or if we're sticking with the normal way of writing that, rationalizing the denominator, it would be the square root of 2 over 2. All right, so we're going to make a sign chart. And we're going to have x values on the bottom, second derivative values on the top. The places where the sign could potentially change are at 0, at negative root 2 over 2, and at positive root 2 over 2. In all of these cases, the second derivative is actually 0. We're going to need to find values in between. Now, square root of 2 over 2 is actually less than 1. So we could use 1 and negative 1 as our values. And then it's bigger than 1/2 though. So we could use 1/2 and negative 1/2 to test for the signs. All right, so plugging into the second derivative, which is probably easier to work with in factored form. So we're plugging into 30x times negative 2x squared plus 1. If you plug in negative 1, f double prime of negative 1 would be 30 times negative 1 times negative 2. Negative 1 squared is just 1, so negative 2 plus 1. So it's going to be a negative times a negative equals a positive. So we're going to have all positives here. And then f double prime of negative 1/2, that's going to be 30 times negative 1/2 times negative 2 times negative 1/2 squared is positive 1/4 plus 1. So that's going to be a negative times, let's see, negative 1/2 plus 1 would be a positive. Negative times positive is going to be negative. Okay, so that's negative. And then plugging in 1/2, f double prime of 1/2 is going to be 30 times 1/2 And then we're going to have negative 2 times 1/4 plus 1 again. So that's going to be a positive times a positive, which is a positive. And then plugging in 1, f double prime rather of 1 would be 30 times 1 times negative 2 plus 1. So that's going to be a positive times a negative. That's going to be a negative. Now, by the way, a lot of times people who just start off with working with sign charts, they think that the sign always alternates like that, but it doesn't. You really do need to check. It's going to depend entirely on the function. All right, so let's see. We have several changes in concavity, right? So at each one of these potential inflection points, it turns out that we do have an inflection point. The function is defined everywhere, so I don't have to worry about excluding any points where the function is undefined. So the function is defined at all three of these values, and the sign of the second derivative changes at each one of these values. So our function changes from concave up to concave down, back to concave up, and then down to concave. So that is the very definition of inflection points. So to answer the question, we have inflection points at x equals 0 and plus or minus root 2 over 2. 3 different inflection points. Now, just to show you that that kind of makes sense, I want to pull up Desmos.com grapher and just show you what the graph of the original function would look like. Okay, so the original function was f of x equals, and then we had negative 3x to the 5th, and we had plus 5x to the 3rd. And I'm going to zoom in a bit. Okay. And what we were observing is that when x is 0, so at the point 0, 0, we have an inflection point. But we also have inflection points at the square root of 2 over 2, comma, I'm not sure what that's supposed to be. Let's see. Maybe negative 1. Oop. Somewhere around there. And then similarly at root 2 over 2, looks like about 1 1/4. We have points of inflection where it changes from looking like it could hold water to looking like it would pour water out. And then of course 0, 0 as well. Okay. Now in the previous section, we were looking for maxes and mins. Notice that the minimums, the valleys, are going to occur on intervals where it's concave up, generally speaking. And the peaks, the relative max for local extrema. So let's talk about that. Any questions though about this exercise before we do? Okay, so let's talk about the second derivative test for local extrema. Or let's call it relative extrema. Different textbooks use those two terms interchangeably. So you can say either. All right, so second derivative test for relative extrema, what it says is that if we have a function f such that f prime of some value c is equal to 0, and the second derivative of f exists on an open interval containing c, then number one, if the second derivative is positive at c, then f of c is a relative minimum. And if the second derivative is negative at c, then f of c is a relative maximum. And that makes sense, right? Because if the second derivative is positive, then what that means is we have a valley, and so there must be a minimum. It's concave up and there's a bottom. If the second derivative is negative, then the original function's concave down, which means that it's a hill and we have a maximum. Now, on the other hand, this test doesn't always work because if the second derivative equals 0, at c, then it may have a relative minimum, a relative extremum, relative min or relative max, or neither. So in that case, you would have to use the first derivative test, where you look at the sign chart for the first derivative. So let's see if we can apply this idea to an example. All right, so let's use the same function that we did in the previous example. And what we're going to do is find any relative extrema of f of x equals negative 3x to the 5th plus 5x cubed. All right, so the only way that we could potentially have a max or a min and use the second derivative to find it is if the first derivative is equal to 0. So remember, our first derivative that we found was negative 15x to the 4th plus 15x squared. So what we're going to do is we're going to find that value c where f prime of c is equal to 0. So we're going to set 0 equal to negative 15x to the 4th plus 15x squared. This again is a polynomial equation, and we want to factor and solve. So we're going to have 0 equals, I'm going to factor out negative 15x squared. You could factor out a positive if you wanted to. Either way, it's going to work out. But if we factor out a negative 15x squared, then in the first term, we're just going to be left with x squared. In the second term, we're going to be left with negative 1. Setting each factor to 0, then, negative 15x squared equals 0 would mean that x is 0. And x squared minus 1 equals 0 would mean x squared is 1, Be careful here to remember you have both a positive and negative square root of 1 as a solution when you take the square root. So x is plus or minus 1. All right, so what we just found in the second derivative test is that value c, where the first derivative is 0. In fact, we found 3 of them, right? So we have 3 c values. C could be 0, C could be 1, or C could be negative 1. These are all potential relative extrema. All right, now we're going to use the second derivative, and we're going to plug in these values and see if we get a positive or negative. So remember, our second derivative, the derivative of the first derivative, is negative 60x cubed plus 30x. So let's see what f double prime of 0 is. F double prime of 0 is going to be 0 plus 0, which is 0. In which case, the second derivative test fails. We don't know if we have a relative max or min at that point. F double prime of 1 is going to be negative 60 plus 30 is negative 30. This means that we have a concave down situation. So there is a relative maximum at x equals 1. F double prime of negative 1 is going to be positive 60 minus 30. So that's going to be positive 30, which means concave up. So that means that we have a relative minimum at x equals negative 1. All right, now I'm not going to check f double prime of 0. I'm not going to check whether that's a max or min using the first derivative test, because we already have the graph and I just want to show you what we have found. So we said we have a relative min at x equals negative 1, a relative max at 1, and we don't know what's happening at 0. So let's look at the graph. Okay, here at negative 1, we said we have a relative min, and you can see that's exactly what's happening. We have a valley. At 1, we have a relative max, and then at 0, actually it turns out we have neither. If we were to do a first derivative sign chart, we'd see that we got positive on one side of 0 and positive on the other side of 0 because it's continuing to increase. It flattens out at 0 and you have a horizontal tangent line, but it's not actually, oh no, I take that back. Oh no, that's right. It's not actually a relative max or min. It's an inflection point, but it's not a relative max or min. Okay, so let me actually grab a picture of this real quick and stick it in our OneNote file. Okay. Put in some labels here. So at negative 1, negative 2, we have a relative min. At 1, 2, we have a relative max. And this one, we have neither, but you would have to do a first derivative sign chart. And your first, to know for sure, you'd at least have to do your first derivative sign chart. So your first derivative sign chart would have the potential extrema on it, negative 1, 0, and 1. You'd see that the function is decreasing, then increasing, then increasing, then decreasing. And so we do not have a relative extrema at 0. We do have relative extrema at negative 1 and 1. Personally, I usually just use the first derivative test, but you need to know what second derivative test is referring to, and this is what it's referring to. Plug in potential critical values into the second derivative to determine if you have a relative max or min. Okay, we're going to end there today unless there are other questions that you'd like me to go over. So take a minute and think about that. Okay, in the meantime, while you're thinking, I'd just like to ask that if you're watching this video that you give it a thumbs up if it was helpful. That helps other students to find the video. It doesn't look like anybody has any questions, so I'm going to go ahead and log off. Remember, you can send me your questions though. Okay. So good luck, and if you have any questions, please don't hesitate to contact me.